Swayam Prabha. Digital India. Educated India.
Good morning, everyone. It is an absolute honor to welcome our guest speaker for today's lecture, Dr. Aamod Desai from the Department of Chemistry at IIT Madras. Dr. Desai's academic journey is a testament to excellence. He completed his Bachelor of Science at the University of Pune before moving to the Indian Institute of Science, Education and Research, IISER Pune, where he earned his integrated master's and PhD. His doctoral research was groundbreaking, focusing on the development of nanomaterials to tackle air and water pollution. Following his PhD, Dr. Desai expanded his horizons internationally as a postdoctoral researcher at the University of St. Andrews in the UK. Today, he is recognized as a leading expert in metal organic framework, porous materials, and sustainable chemistry. His work as a battery scientist is particularly vital today as he focuses on making battery materials more environment friendly and affordable for a greener future. With over 10,000 citations and a wealth of experience in solving real world environmental challenges, through chemistry, we are incredibly fortunate to have him share his insights with us today. Sir, we are eager to learn from your expertise. Without further ado, please join me in a warm welcome for Dr. Aamod Desai as he takes the floor for today's lecture.
And good morning to all of you. My name is Aamod Desai, of course, now you know. And I'll be talking about something called as Nanospace Navigation. And I would like this session to be a bit more interactive. Like, I want to know the ideas that you have about these terms and the terms that I explain as we go along. So I would expect a few answers from you whenever I have a question posed on the screen or I ask you in general. So what do you understand by the term nanospace and navigation? Just throw in some words. What is nano? Let's break it down. What is nanospace? Nano nanoscale is the word. Yeah. Okay. So we're talking about nanoscales, right? So let's say I'm explaining everything in terms of nanometers. So what is 1 nanometer equal to in terms of meters? -9. So if I just keep going down the scale or going up the scale, so what are the typical terms that you know? So what is 10 to the power -6 meters? Micro. So it would be a micrometer and millimeter. Keep going down. Picometer. Yeah. Femtometer. Now, if I ask you what is a nanomaterial, what is a typical length scale that I'm looking at? 1 to 100 nanometers. So roughly somewhere in this region, like not touching this part, but like somewhere over here, right? So today's presentation or the materials that I discussed today are essentially going to be part of this region. Can you see them by your naked eyes? No, right? You need some kind of a microscope. What kind of microscope do you think is required here? Can you use the optical microscope that is electron microscope? So some of you have heard about electron microscopy, right? So the talk or the presentation in general would have some of the electron microscopic images and analysis that we do. Now let's come to the second word, navigation. What do you understand by the word navigation? I'm sure everyone has used Google Maps. So everyone knows what Google Maps is and how it functions. But what essentially it means to you, essentially, what is navigation? Any answer? Finding direction. Any other? Getting to one place to another. So basically, what we are going to do is try and navigate in this particular region. And the idea is how do we do that is first construct those materials, find those spaces where we can navigate, and essentially go in and then start navigating, essentially use Google Maps at nanometer level. This is kind of this overall idea. So let's come to the length scales in general. Like all of you have already told me what electron microscope is, but just to put everything into context, why this is so important. Milky Way is 1 lakh light years is typically the estimated distance or the length of the Milky Way. Does anyone know why Milky Way or space objects are calculated in terms of light years and not in terms of the metric scale? Okay, maybe go one by one. Yeah, someone. Extremely large distance. So light is the. Okay. Any other answer? Yeah. to travel. Okay. Yeah, you had something to add? Brilliant, brilliant, brilliant. Good, all good answers. So essentially, this is the only thing on the slide which is measured in terms of light years. Does anyone know the diameter of Earth? Of course, everyone knows, but does it? Let's say roughly 13,000 kilometers, right? Yeah, some 12. I don't have the exact number. Roughly 13,000 kilometers. I have a home in Chennai. What is the length of my home? A bungalow? I don't have a home though, but let's say I have a home in Chennai. What is the length of this bungalow? Typically, what would you guess? Not the carpet area, just the length of a bungalow. Sorry, 12 meters? What? 100 meters? Sorry, I didn't hear that. 12 feet? Okay. So let's say I'm rich. I have a big bungalow. It's let's say 10 meters, right? So I'm going down the scale now. I've gone down from 13,000 kilometers to 10 meters. A lot of you play football or have seen football. What is the estimate of a diameter of a football? 20? 20 centimeters, roughly. Everyone can imagine a football, 20 centimeters. Now, an insect, you'll see a lot of insects in this campus, let's say has a size of 1 centimeter. Now, a lot of you have papers, right? What is the thickness of that paper? 0.1, 1 to 1 millimeters, right? So essentially now, all of these are visible objects. But what happens on this bottom scale? Essentially, we start going into micrometers, nanometers, subatomic particles that are even smaller. We go to picometer and femtometer, right? Essentially, the top panel is the things that we see with our naked eyes. The things in the bottom panel are essentially we don't see with our eyes. And because we can't see them with our eyes, we essentially need some techniques by which we are able to visualize them. RBCs, viruses, everyone is familiar with this virus now. For some reason, this DNA is not showing here, but this is a DNA, this is an atom, and then we go to subatomic particles, right? And there is a lot of interest in scientific community to understand and visualize what subatomic particles look like. So at the moment, there is a good deal of work going on to visualize what subatomic particles look like, how big they are, and how do they behave. Because we are kind of fairly sure what happens until this region. We kind of understand what happens there, but have people heard about the experiment at CERN in Switzerland, where people are having Large Hadron Collider? Yeah, essentially the idea there is to look at the subatomic particles and what happens in the nucleus and what is the consequence on the behavior of the electron in the subatomic particles, right? So everyone now has a good understanding of the length scale, right? This is the idea of length scale, and today we are going to focus only on the nanometer region. So before I go to the discussion, I want you to tell me, I have a cube, right? I have a cube, the length or one side of it is A. What is the surface area for this cube? 6A square, brilliant. So now I have a cube which has a surface area of 6A square. Now, everyone is familiar with this idea that objects or matter behaves differently at the nanometer level compared to the bulk, right? And why is that so? Let's say people have used this analogy of gold having glittering yellowish color in the bulk, but if you make a nanoparticle of the gold, it has a reddish, or you can have different colors. You can have a red colored solution of gold. Why do they tend to behave differently at the bulk versus the nanometer level? Structural arrangement. Any other answers? Area and volume scale differently. So let's try and analyze this. I've got this particular cube which has a surface area of 6A square. This is the total surface area. Now for some reason I decide to chop it into half. By this way, I have this way and all the three axes. Essentially I'm chopping it half this way. How many smaller cubes have I formed in this process? 8. So now can you calculate the surface area that is available? I've got 8 individual cubes. Each cube now has a length of A by 2. So what is the total surface area? 12A square. Everyone is able to follow this one. We've got now a cube with a length of A by 2. So the total surface area is going to be 12A square. Now I decide to further half it down. I have another piece of knife and I just break the cube even further. I have a cube with a edge length of a by 4. What is the total surface area? Everyone's able to see 24a square, right? So we've got 24a square. Now what happens to the volume? What is the volume of this cube? The first cube, the original cube, a cube. What happens to the volume of this one? So now if we do surface area by volume, the number is going to go up, right? So essentially we are not changing the volume of the piece of the cube or the matter that we had, but the amount of area that is exposed is now going to be much higher. And a simple way to visualize this is this Rubik's cube, right? Essentially you have the full cube as your original cube. You just break it down into 4 pieces. You make it into a by 4, and now there is 4, like whatever, 64 or more than that number of cubes that are part of this. And each of them now have got slightly higher surface area. So you can take apart each of these individual cubes. So the total surface area that you're getting is 24a square, whereas the total volume that you get from all of these individual pieces is going to be still a cube. So the surface area by volume ratio is going to go up drastically. You're cutting this down by half. You're going from a to a by 2, but you're increasing the surface area by twice. But then you go further 2 times, you increase from the original part 4 times. So you kind of have dramatic increase in the accessible surface area. Now essentially this is what is happening when we go down from an object in the bulk, which we can visualize, to an object in the nanometer region, which is having slightly different properties. So the surface area that is accessible is now going to be much, much higher. Everyone fairly comfortable with this idea? Good. So now what we do is we try and understand porosity. Let's see how many of you are aware about the term porosity. Any examples of porosity that you see in your daily life? Sponge, yeah, of course. What is this, by the way? Mastic. Why does a mastic have porosity? We'll go one by one. I can't hear otherwise, sorry. Let's start from one here, one from there. Oxygen, access to oxygen. Any other reason? Why do you think matchsticks have porosity? High surface area, of course. Yeah. Sorry. Rough texture. The other reason is, like, matchsticks typically have a waxy substance that is sitting next to the wooden part of the piece. So to have access to that waxy piece, which essentially burns, we need oxygen to go through it. And this is the reason why we typically end up having pores in the edge of the matchstick, right? And for a fire to, like if you have to stop a fire, if you have been designated to stop a fire, what is one way to do it? Cut the oxygen, right? So essentially, if you have an environment where the matchstick doesn't have holes into it, you sometimes struggle to burn it. And when does that happen? When you have got high humidity. So essentially, the holes are now blocked by moisture molecules or water molecules that is not allowing the oxygen to go and reach the waxy part, which essentially burns. So this is a very good example which we see in our daily lives. Of course, all of you have said about sponge, right? And I want you to go back home today, or whenever you go back home, next is just try this experiment once. You just take a piece of sponge, put it into a bowl of water, force it, like literally force it, which we usually do, but hold it underwater and then press it. And in the second experiment, don't press it, just keep it underwater. And what you will see when you just don't have exert any pressure, you do get water inserting into the voids of the sponge. But essentially that is a very slow process. The moment you kind of force it or squeeze it, there is a lot of air bubbles that come out from it, right? So essentially the entire void that is present in the sponge is occupied by air, and water kind of goes and replaces this void molecule. Very simple, right? It is nothing rocket science here. It's very basic and very simple. But why this is important is now we have to start visualizing this at the nanometer level. Because this is an experiment which we always see with our eyes. We are very comfortable with this idea that air occupies this, water goes and replaces this. But it's almost impossible to visualize it or see it when it happens at the nanometer level. But at the end of today's lecture, I hope some of you will be able to appreciate this idea, what comes next. So some of you said porosity exists in sponge. Any other examples that you can think of? We have seen a matchstick, we have seen a sponge. Any other examples? Stone, brilliant. We have got a stone. If you go to the coast, you sometimes have some of these stones. Why do these stones have holes, by the way? lightweight, okay. Uh, Erosion, float, micro, yeah. When they were forming, you mean? Okay. What about this one? Do people recognize what this is? Why do cheese blocks have holes in them? Sorry, could it be louder? Right. Okay. Okay. What about this one? We all are testament to this, right? We have pores, that's why we are sweating so much in Chennai. So if we didn't have pores, there would be a lot of water that gets trapped within us and we are not able to cool down, right? The moment we start sweating, we are essentially letting our bodies cool down, and this is kind of the outlet. This is a very good example of how porosity works in something within us, but which we are not able to appreciate it enough. Okay, so let's come to this idea of length scales one more time. So I've got this chart over here that explains three types of porosity. The examples that we saw, sponge, stone, cheese, all of that is essentially part of what is called as a macropore, right? So this is part of the macropore, which starts from roughly 20 to 30 nanometers, goes up all the way up to the part where we can visualize things. If you go down below that, you start going into the domain of mesopores. Mesopores are typically sub-nanometers, like 1 to 10 nanometers. If you go even further down, you start going into the domain of micropores, which is roughly 0.1 to 1 nanometers. Right? Now, when I'm talking about nanometers, can someone give me an example of what region are we talking about? Any entity that you know that we are talking about? Sorry? No, not the relation to meter, but some chemical entity that you can think of when we're talking in the domain of nanometers. Crystal lattices. If I ask you about a carbon-carbon bond, what is the bond length for a carbon-carbon single bond or carbon-carbon double bond? 1.5, let's say, somewhere in this region. This is angstrom. So what is it in terms of nanometers? 0.154. Now, the porosity that I'm talking about, which is micropores, is essentially the porosity in this domain. So you can imagine how small the pockets would be. I'm just talking about a carbon-carbon bond length, which is roughly this region, and the microporosity that I'm talking about is in this area. Now, there are a couple of images coming up, and I want you to tell me some differences that you see. The one on the left is electron microscopy image of iron oxide. Don't worry about the rough part at the back. That is essentially the background used for preparing the sample. The iron oxide particle is this globular shaped, nice smooth surface. This is, look at the length scale over here. The length scale, this much corresponds to just the 10 micrometer. The second image on the right is of a cotton fabric. Now, cotton fabric has got this fibril nature, so it has got these strands that go parallel to each other. The length scale here is 300 micrometers. So now we have got two different objects seen under the electron microscope, which have got slightly different length scales and textures. Any other things that you see different between the two of them? Sorry? Edge, okay. Roughness and edge. Roughness, okay. Roughness is different. Any other things that you see different? Shape is different. Perfect. Yeah. Just try and connect it to the thing that we were looking here. Size is different, of course. That's very true. What happens in terms of porosity? Do we see any empty space here or any holes here? Sorry? Spaces between the fibrils, yeah. But in this case, there is no space, right? So this is now an example of a dense particle, a non-porous particle. That is, even at this particular level, when we go to nanometer level, we don't see any holes or empty space. Whereas on the thing on the right, because cotton is something that we wear and we observe that has some porosity, when you visualize it under the microscope, you see that there is some empty space or for objects to travel between the strands. And you can see this empty space that is there on this length scale. So there are two things. One of them is the idea of a non-porous nature, And someone rightly said that this has got a smooth surface, this has got a slightly rough surface, and the other part is the length scales. So now we have touched upon the idea of nanometers, we have touched upon the idea of porosity, we have touched upon the idea of surface textures, right? Okay. Now what is the other thing that I want to link here is among the two things that we had there, right? We had iron oxide and we had cotton. One of them was non-porous, the other one was porous. So what happens in terms of densities? High density is iron oxide, low dense material. And what happens in terms of volumes now? If I have the same, two objects of the same mass, this will have lesser volume, right? So lesser volume. Much higher volume. Now, you might think that I'm just asking you very simple, easy questions, right? But there's a good reason for doing so. The moment we have got this property, we start seeing differences in terms of densities. Now, densities is something that you already know and you're very familiar with. Can you give me some examples of things that have got different densities? Anything in your everyday life? Water and oil. So if I take a mixture of coconut oil and water, what will float on top of the other? Oil floats on water. Okay. Any other example? Cotton and something. Cotton we are wearing, iron oxide or any metal particle. You go to a trip, you bring back a fridge magnet. That could be considered something like a metallic particle, right? So if you compare that versus cotton, of course, cotton is going to be much lighter. So it's going to have much lower density. Any other examples that you can think of which have got slightly different densities? Sorry? Mercury and iron will float on mercury. Is there a reason for what? Why mercury has low density? Mixture of gases in the atmosphere. Can you give me two examples of gases? Which one is lighter, which one is heavier? Sorry, helium? So let's analyze this one first. Gases, mixture of gases. Oxygen, carbon dioxide. Which one is heavier? Carbon dioxide. Okay. Any other examples? Helium and argon. Which one is heavier? Argon is heavier. Yeah. Come back to the metal part. Mercury and iron. Which one is heavier, lighter? Mercury is heavier. Okay. But more dense. And where do you see mercury in your everyday life? Thermometers. Brilliant. So now we have a fairly good idea about what density does to objects, right? So essentially we have got two different types of, if we have got a mixture, we essentially have densities separating them between either could be just one layer stacked on top of the other, or if we have got a mixture, they essentially separate out. In terms of gases, we can see that they're fused together if it's a gaseous mixture, but the moment we have got some pressure differences, we are able to separate them. Now, have people seen this? Not at Barbecue Nation, but somewhere else. Activated carbon, right? So essentially, we for the production of metals, right? Yeah, that's true. But this is essentially chunks of activated carbon. And activated carbon essentially is kind of all of this. It has got low density, it has got some porous properties, and it has got, like, it occupies some volume. But the most important thing with what this does is essentially trap organic matter. Is the porosity that is present in activated carbon is able to interact with the waste in some dye molecules or any water pollutants, and it is able to absorb it. So I'll just write the term that I'm saying. It's not absorb, it is adsorb. So all of you are familiar with the term absorb. So the experiment that I was referring to when I said go home and try the sponge experiment, when you put a sponge in a water solution, the water occupies the air that is present in the voids, and the process is called absorption. Because the moment you take it out and squeeze it back again, all the water molecules come out. Now what happens in the case of adsorption is there is some kind of interaction that happens, and this particular sorbent is now able to trap any of these organic matter. And this is not something that is very unfamiliar to you guys. Some of you have seen water purifiers at home, right? And in one of the water purifier, in all of the water purifiers, one of the columns is essentially something over here, which is the carbon filter, right? And this carbon filter is nothing but activated carbon. And it is essentially required for trapping some pollutants that are present in the drinking water sources. So now what we are looking at is activated carbon, which has got sub-nanometer level pores, is now able to trap water pollutants. And this happens by the process of adsorption, not by absorption. Now, the reason why I'm saying this is, in this particular case, if you take 1 liter of polluted water, you just pass that 1 liter of polluted water through this Kent RO or any RO purifier, whatever comes out will be 1 liter of water. What this particular carbon filter is going to do is essentially going to trap only the pollutants. Now think of this experimentally different to the first part that I described. You take a bowl of water, put a sponge inside that, you press it, the sponge absorbs all the water. The moment you lift the sponge up, there is going to be a reduction in the volume of water. You press it back on, all the water comes down. That is a different thing. But the process that happens is absorption. Whereas for the case of activated carbon, what it is doing is essentially adsorption. It is able to trap pollutants and it is able to release or let go of the water that passes through it. So this is one example. Have people seen this one in the Amazon packets or something? Typically we get this silica gel thing, right? What is the function of this thing? Moisture, trapping moisture, and it says it is silica gel, right? So what kind of function is it doing? Yeah.
So activated carbon is just heated charcoal. Right?
Heated charcoal.
So then how does heating it change its porous?
Heating is not changing the porosity. What it is doing is essentially emptying the pores. So the sponge comes with air filled with, right? Basically it is clear of it. But because activated carbon has got some interacting sites, if you let it out in this particular room, which has a humidity of 59%, it will start absorbing water. So to clear all the pores out of it, we essentially need to heat it up. So it is just essentially activating is kind of clearing all the pores, so that is now able to access and do that function of adsorption. Yeah.
Are there other forms of activated carbon?
Activated carbon is amorphous material. I'm coming to that. I'll answer your question, right? So anyone knows how the function of, or what the function of silica gel is? Absorb moisture, but how does it do it? Sorry? Moisture sticks to the surface. And what is this packet made of? Porous material, right? So now this porosity is going to be much bigger or greater than the porosity of the silica gel. Otherwise, silica gel starts coming out from here. But the moisture is able to transport through this one and then be trapped into the silica gel matrix, right? And again, the two things that I want to touch upon here is silica gel and activated carbon. Both of them are crystalline or amorphous. So let's talk about activated carbon. Crystalline or amorphous? Amorphous. So I've got activated carbon, which is amorphous, and silica gel. Silica gel, crystalline. Okay, let's put a question mark here. Let's try and answer this one. So any other form of silica that you know of? Sand. Okay, sand is a good answer. What happens with glass? Brilliant. So is glass crystalline or amorphous? What do you think? Amorphous. Okay. And what happens in silica gel? So essentially, it is also an amorphous phase of silica, right? And everyone is able to appreciate the idea of amorphous versus crystalline. Okay, I'll ask, what is a crystalline material and what is an amorphous material? One by one, please. Yeah, sorry. Yeah. Well-defined architecture, and amorphous does not have a well-defined architecture. Any other answers? What would you differentiate crystalline versus amorphous? So geometry is well defined in the case of crystalline. In case of amorphous, it is not well defined. Okay, so essentially we have got two substances that are amorphous in nature, but that we use in our everyday life as for the function of adsorption and for the function of absorption, right? So this is a few takeaways from this part. Now, activated carbon, as I said, it is able to function as an adsorbent because it has got some porosity within it. And as someone rightly mentioned, that we need to heat it. We essentially need to activate it. That's why it's called as an activated carbon, to clear all the pores that are present inside, right? So essentially, this is an example of an activated carbon, which is a porous material. But any of you know examples of porous materials that are there in nature, not man-made? So let's say cotton fabric will be kind of somewhere in between, right? We obtain cotton from nature, but we make a t-shirt out of it. Honeycomb structures, brilliant. Any other? Sorry? Pumas, okay. Any others? Soil, soil with example of that? Any soil. So now I'll show you one more example. Have you heard of this term, zeolites? Zeolites, anyone? No, yes? No? Okay. So essentially, zeolites is a matrix of 3 atoms. Essentially, it has got aluminum, silicon, and oxygen, and they kind of combine to form this long-range architecture, which looks very symmetric. Now, silicon and oxygen are examples that we already looked at in silica gel. We looked at the example of sand. We looked at the example of glass. Aluminum is also one of the more abundant elements in Earth's crust. So what nature did for millions of years is essentially try and combine and form a very symmetric architecture based on this. And you can see that the architectures have got this empty channels in between. And these empty channels are able to be accessed by some molecules which go and interact with it. And in terms of natural representation, they look something like this. So if you go to a museum, Chennai's Science Museum or any other museum, go and see some of the sections which have got crystals. And when you go to the sections which have got crystals, try and look at the names for it. And then use Google or something to understand what that name is. You'll find out that a lot of these crystals, which look very long and sturdy, are essentially zeolites that are grown in nature. And these crystals are essentially grown over millions of years. This is kind of the thermodynamic product, right? It is not grown suddenly. It is grown over millions of years. So it is a very slow reaction that leads to the formation of zeolites. Zeolites are one very common class of materials that are used in organic labs. So if you go around this building in some of the research labs, you will find that zeolites, not in this form, it's in a different form, are used in the labs. And the main purpose of using zeolites in labs is essentially to trap moisture. So you'll be surprised the function of this. So if you take a zeolite particle, put it into an organic solvent. Let's say I have got a solution of benzene, which is liquid in room temperature, and there is some moisture molecules that are floating around in the benzene. I need to purify it. One of the nicest and easiest way is to just take this zeolites, which has got this empty holes in between, put it into a solution of benzene, and it is able to trap all the moisture molecules. And this particular zeolite is not going to react with benzene at all. So if benzene gets purified, this is inert to benzene. So essentially you have purification within no time, and it happens with no extra effort. So if you go to any of the research labs, you'll find a lot of zeolites lying around in each of these labs, used for this is one of the functions. But if you go to industry, these are used for catalytic applications also. You take one organic molecule, you pass it into this particular pore or this empty space, you have catalytic conversion going on, and then the product comes off and the zeolite stays intact. So again, this is a highly important class of materials. So if you talk to any chemist or any particular person working in the area of porous materials, these are the 2 classic examples they'll always tell you. One of them is activated charcoal or activated carbon, which is essentially an amorphous material, but it is used in our daily lives for a lot of different things. And one of the common things is to purify pollutants from water. The second example is of a crystalline material. So this is amorphous, this is crystalline, and a crystalline material is able to have well-defined architecture. It is able to grow crystals, and it is used for a lot of different things. Right? Let's come back to atomic bonding just before we finish this topic. So I've shown an example of iron oxide, right? And this is a crystal structure. So essentially I'm using electron microscopy, I'm using X-ray diffraction, all of those techniques to understand the crystal structure of iron oxide. Now in the crystal structure of iron oxide, iron has an ionic radius of 77 picometers. oxygen or oxide has an ionic radii of 126 picometers. And it just kind of looks something very periodic and crystalline in nature. Now, remember the image that I showed you before of the electron microscopy image, right? It had this globular shaped, it had a smooth surface, it did not have any cracks, it did not have any empty space. And the reason for this is the structure. It is so very stable, it is so very rigid in some sense that there is no empty space, so there is no creation of holes or porosity. There is perfect binding. All the iron coordinations are satisfied, all the oxygens are present next to each other. So it is a very rigid structure in some sense. Now, what I wanted to ask next is, what are the types of bondings that you know of? If I have got, yeah, ionic covalent, any coordinate bonding, okay, brilliant. So let's say I've got atom 1, I've got atom 2, they're kind of combining together, and it could be molecule 1, it could be molecule 2 also. So all of you have given really good answers. So you have said it is about ionic bonding, covalent bonding, coordinate bonding. Any other examples? Metallic bonding, H bonding, yeah. So now we'll go one by one. What happens in the case of ionic bonding? Donation of electrons, or is there a donation, or is there just an electrostatic interaction? Electrostatic interaction. Any example? NaCl, brilliant. So NaCl, there is some electrostatic interaction. Covalent sharing of electrons. Any example? O2, Cl2, O2, okay. Coordinate bonding? Sorry? Ammonium, okay. What kind of bonding are we looking at in the case of coordinate? We'll go one by one, yeah. One element will give 2 electrons. Any other example? One?
The sharing is responsible only by
One of them. Any examples for this one? Ozone. Okay, we'll go one by one. Ozone, yeah. Ammonium ion. Any bicarbonate? Okay. Sorry. BF3. Okay. What happens in the case of metallic bond? Metallic bond, anyone? Lattice. Okay. So I've got metals present everywhere, and the electrons are kind of stuck in between somewhere. Delocalized. Electrons are delocalized in some sense. What happens in the case of H bonding? Yeah, maybe one more. Okay, so I've got hydrogen that is connected to a donor group, let's say. It has got a delta positive charge. This has got a delta negative charge. There is some attraction, right? So in all of these examples, what is the relative strength that you think of in terms of bonding? So let's take the first two. Let's metallic bond is slightly hard to put it into the same basket, so we'll exclude metallic for the moment. Let's compare ionic covalent, coordinate, and H bonding. Which one will be the weakest in some terms of strength? H bonding. H bonding, because it doesn't have essentially a direct bond that forms. It has just got some very weak attraction, right? So H bonding will be the weakest. So let's give it like W for this one. Which one will be the strongest? Sure, everyone? Will I, if I take sodium chloride and put it into water, what is happening? Dissociation. Is it easy for me to break oxygen molecule? If I have to break even nitrogen, right? Let's say, if I have to break oxygen, if I have to break nitrogen, do I, sorry? Sorry. Triple bond, yeah. But even if I have to break, let's say, oxygen, it requires some strength, right? But it's easier to break the sodium chloride bonding because I can put it into a solution, it kind of dissociates very quickly. So in terms of bond strengths, this will be having some of the covalent bonding are pretty strong. What happens in the case of coordinate bonding? Any ideas? Sorry. Uh, uh, yeah, could you repeat that? Similar to covalent. Okay. So essentially, it is kind of somewhere in between. So if this is stronger, this would be kind of, this is S1, S2, S3. Maybe I'll put it as S4. So in terms of bonding strengths, right, covalent bonds are pretty stable, pretty strong. Coordinate bonds are kind of similar to covalent bonds, but they've got slightly lower tendencies or lower strengths. Ionic bonds are not that far. It's not like I'm saying this is miles ahead of the other one, but ionic bonds are fairly easier to break sometimes. But in case of hydrogen bonding or any non-covalent interaction, it could be electrostatic, pi-pi interactions. Have you heard of pi-pi interactions? Pi-pi interactions, hydrogen bonding interactions, all of those interactions are fairly weak. So why this is important is we'll come back after the break and then we'll discuss this in a bit more details. But try and hold on to this thought of different types of bondings. Covalent compound, there could be an example of a covalent compound that is weaker than ionic compound, but the bond energy strengths, it is much wider. So for example, you can have, let's say, some of the ionic compounds that are slightly stronger than the covalent bonds, but for majority of the covalent bonds, they are expected to be stronger than the ionic bond. Yeah. Any other questions until now? Otherwise, we just take a quick break and then we resume after that. Yeah. The average size of pores in zeolites is roughly in the region of 5 to 10 angstroms. It is again something very similar to what activated carbons have. But the main feature about zeolites is the property to essentially tune this. So this has got a cylindrical pore. In the case of activated carbon, we don't have a clue what kind of pores it is. You can just essentially change the structure. Instead of SiO groups and ALO groups arranged in this particular fashion, you can have a central group that is different. You essentially start changing the pore character. Instead of having a cylindrical shape, you can have a square grid shape, or you can have some other shapes also. The thing with natural zeolites is most of them tend to form as proper crystals. So you're able to understand the crystal structure based on the possibility of growing crystals. Any yeah. Amorphous materials can be stronger. It's not that they are not strong. Glass is pretty strong, right? Sodium chloride is an example of a crystalline material, but that is kind of easy to break. Glass is fairly strong, so it is not impossible to have that. The main feature comes in the way we look at the physical properties of them or any chemical properties that arise because of that. Yeah, if there are no more questions, we'll take a quick break now and then we'll resume after the break.